Today I'm gonna introduce you some self-supervised learning in human activity recognition. And this presentation mainly contains 4 parts. In the introduction part, I will introduce you some background of this human activity recognition. And more importantly, the main topic of this presentation is the feature extraction and self-supervised learning. And in the second part, I will introduce the 5 recent methods addressing the self-supervised learning in this human activity recognition. And the third part is experiments should how they perform in this kind of task. And the last one is conclusions and discussion. In the first introduction part, first we should define the human activity recognition. Here I define it as a task utilizing sensor data to recognize human activities. Here the sensor data can come from the visual images, videos, or motion sensors like cerebromotor or gyroscope. And in this presentation, all the methods will focus on the motion sensors. And a common activity recognition chain adopted by lots of papers can be decomposed as signal processing, feature representation, and the classifier. And the signal processing is almost done at the data collection phase, like denoising. So if we are using the public data sets, like user HER, we should not very care about this part. And the classification performance will highly depends on the feature representation. I will give you more details about this part in the following presentation. And for the classifiers, we can use a lot of different classifiers. Some traditional machine learning classifier like SVM or some as a kind of like a forest, okay, a random forest. But generally, this machine learning based classifiers present the best performance now. However, it will depend on more labeled data. And many works recently explored some feature extraction techniques, because this part is very critical for this task. And some adopt statistic features like using the mean standard deviation or for the frequency domain features. But more recently turns to find better learned features that derive representation directly from the raw sensor data themselves by using some machine learning techniques. And one question, one subfield in the feature extraction is to try to answer following question: how to learn good features using unlabeled data, like what I'm going to introduce next. A hot and promising solution is called self-supervised learning, which is first termed by Ian Lecken in 2018. The idea is to leverage data's inherent co-occurrence relationships as the self-supervision. And the relationship with unsupervised learning is that this SSL can be regarded as a subset of the unsupervised learning, but it will utilize a portion of the input as a supervisory signal to get the model to learn more meaningful features for another part of the input. And there are triple motions. The first one, first two, like other unsupervised learning, they try to utilize the tremendous available unlabeled data and save the time and the resource for the data annotations. And the third part comes from because of this task, human activity recognition. Most times, those data are generated from personal devices like wearable devices. And so it also involves these privacy concerns. And generally speaking, this self-supervised learning has two stages. The first stage is to pre-train the encoders in defined pretext tasks. This pretext tasks can be different and is very critical for this SSL. And another part is just like the other transform learning apply the frozen encoder to the downstream tasks. And for further to help you further understand the pretest task, I also list some examples in the computer vision and NLP fields, such as in the computer vision, some tasks may like image rotation prediction or masked patch reconstruction or relative position prediction. All those tasks can be regarded as pretest tasks. And in the NLP, a very famous task is next word prediction, like or other like the mask reconstruction performed by Google's BERT. And those tasks can also be regarded as pretest tasks. So generally speaking, this self-supervised learning is a feature extraction scheme using unlabeled data. And here I give you a figure to show you the evaluation of feature learning approaches from handcrafted measures towards to the task discovery for the self-supervised supervision. And in the manual feature extraction, it requires domain-specific knowledge. It varies with the type of applications and the formats of collected data. And the second one, autoencoder, can generate the features from the encoder. And in some researchers' opinion, it can be also regarded as one type of self-supervised learning. And the third is well-used end-to-end learning. It doesn't explicitly represent the features of inputs, but a part of the model can be seen doing the feature extraction as well. However, in the self-supervised learning, the model is directly divided into the encoder and the classifier. In the stage one, the pretext tasks are performed to train the encoder, and the features outputted by the frozen encoder will be used in the downstream tasks, such as classification. And let's see some self-supervised learning measures in HAR. The key question for the self-supervised learning is that how to get meaningful representation in the pre-training stage. The equivalent question is how to design the pre-task tasks. Generally speaking, it's still an open question, either for the computer vision or for this new field, human activity recognition. And here, I only some solutions can address this problem, like you can use GNN autoencoder or a promising method like called contrastive learning. Here, I only include some critical notes about the contrastive learning. The goal of it is to train the encoder, making the similar. We also call that positive pairs of data points, make them closer, and the similar negative ones orthogonal in the latent space. And a common, also those different methods in contrastive learning may give us various ways to construct positive pairs and negative pairs. They generally use very similar objective function called info-NCE. As the from this equation below, we can see that it is quite is kind of a variant of softmax function involving the positive pairs and the negative pairs. For example, here the x and the x plus represent can form a positive pair. The x is the target data, and x plus is the similar one. It can be generated from some transformation, or it can be in the same sequence of the target data. So generally speaking, those two those positive pair should have very similar or co-occurrence relationships. And let's say some existing works applying the SSL in HAR. The first one I want to introduce is multitask SSL. The figure 2 is the overall architecture of this model. We can see that it follows the two-staged patterns. The stage 1 is the pre-training stage. In this stage, it is multitask learning. It means those are many classifiers, many heads. Each head is to detect whether the input is performed by a specific transformation. So we have raw data, and we will randomly, we will know the specific transformation tab, and we apply those transformation tab to the raw data, and the transformed data will be the input of this model. And one head or one classifier, the goal, the mission of this classifier is to detect whether the input is transformed. So there are totally T detectors corresponding to T different transformation. Like you can add in some noise, you can scaling the magnitude or flapping the time series signals. And all those tasks should share the same encoder, which consisting of, in this work, they use 3 convolution layers, but you can change it and other layers to do the encoder, or to do the encoder's job. And in the downstream task, the frozen encoder from the pre-training stage will be fine-tuned to predict the activities. So in the stage 2, it's just like the supervised learning. You give the raw data and to predict the label of this input. And the second method is called convolution autoencoder. The figure 3 show you the overview. Actually, it's a simple implementation of autoencoder. Here, the input consists of individual frames. Here, they use 1 second. For example, if the sampling the sampling rate is 5 hertz, you will get 5 samples from each channel or each sensors. Because here, generally here, the raw data will have 6 sensors readings, accelerometer and gyroscope. Each of them have X, Y, Z axis. So this is the input. Actually, this scheme is applied to all the methods I introduced today. You can also use different input scheme, like you can use the frequency. Like before, I read a paper named Deep Sense, they use the frequency, but here they all use the time series signals. And the encoder will consider each this input as a single channel image, so they can use the convolution layer. And the encoder contains like 4 convolution blocks followed by a full connected layer. And the vectors outputted by the FC is the nerd features that will be used in the downstream task. The third method is called masked reconstruction SSL. And the input actually this work is very similar to Google's BERT model. In the pre-training stage, the input is same as the last method. Is 1 frame that contains T consecutive n dimension sensor. Here n equals to 6 readings, and 10% of the samples in each frame will be randomly masked for all dimensions. And the task, the pre-test task is to reconstruct the maxed out parts and those to know temporal patterns from the context. And the encoder here, they use the transformer to obtain some representation at each time step. And then they use a max pooling layer to generate the representation for each frame. And the method 4 is named contrastive predictive coding, CPC. As the name tells, the pretest task involves contrastive and predictive. Specifically, you can have a look at the figure 6. It's the architecture of the pre-training model. And from the bottom to top, the raw time series signals are segmented into fixed frames. Let's see, 1 frame we include like L time steps, and the data in each time step consists of readings from 6 sensors. And passing this frame data through, they use 1D convolution layer, and we will get the Z vectors. The number of Z vectors in 1 frame is still L. So they can use RNN to generate the contrast vector here, CT. And then they will pass the CT into a prediction network. Here they just use a linear layer to predict the z vectors in the future. So here the predicted vector W1 to W4 will corresponds to the ZT+1 to ZT+4. So those like W1 and ZT+1 will form a positive pair in this context. So let's talk about the fifth method. Also, it's the state-of-art method, which is contrastive self-supervised learning. This work is inspired by augmentation techniques widely used in computer vision. The main idea is to randomly perform two different augmentation methods to one input. Say like the rotator X1 will have two augmented versions, X11, X12, and those two will be regarded as a positive pair. And that's the idea. That's how they construct or design the positive pair. The final part is the experiment. The data sets using in the experiments include USHAR, USHAD, and MOBI-ACT. Those are very popular public data sets in human activity recognition. And here I list their number of users, their number of activities, and their sampling rates of the device. And we can see that those factors, this difference will actually will affect the effectiveness of the methods. So considering the heterogeneity among those data sets is also a very important topic, but it's not in our discussing now. Also, they have different users activities, but they all use the raw features, include XYZ for the accelerometer, XYZ for the gyroscope, and also the train wet test slab is the same. It's a subject based split. They use 20% of subjects in the data as the test data set, and 20% of the remaining subjects data will be in the validation test, and the remaining are training test. And in terms of the data pre-processing, because they all use the machine learning model, say, so they all think they should apply very simple data processing that will also work fine. So here they just downsample all the raw data to 13 hertz. Actually, this number 13 hertz will vary in different papers. How to choose the appropriate sampling rate is unknown. And also they segmented those raw data into 50% of overlapping time windows of 1 second length. And the performance metric here use mean F1 score given by this equation, where the C corresponds to the number of classes, while the pre-C and the record C are the precision and the record for each class. The mean F1 score is more suitable than the accuracy here. to evaluate the performance of models, especially in the unbalanced data sets. And except from aforementioned 5 SS measures, 2 supervised methods are also included in the comparison, like deep conv LSTM. It's just a stack of convolution layers and LSTM. And the transformer, this transformer is the encoder in the CSS HAR. They have the same architecture. And those 2 models are directly trained in the supervised manner using all labeled data. And the experimental procedure for the SSL measures include 3 parts. The first one is to pre-train the encoder with unlabeled data. And you freeze the encoder to add basically they all use the MLP as the classifier. It's simple, but it's powerful. And finally, we compare the mean F1 score for the test data set. And we can see here, this is the results for the classification performance. Figure 8 shows us the F1 scores for those different measures. The SUP here denotes the training the model in the supervised manner, and the SSL denotes the training the model in the self-supervised manner. And we can see from the figure that given the same encoder and enough labeled data, the performance of supervised learning decides the upper bound of the performance of the self-supervised learning. Because you can see the results from the transformer in 3 data sets are obviously better than the CSS HAR, even they have the same architecture. The second conclusion we can get is that CSS HAR is the state-of-art method, which improves 9% and 5.75% from previous measures. And you can see for the UCI HAR, it has like 10% improvement. Is quite high for this task. And also we can see that compared to the supervised model, deep conv LSTM, this CSS HAR also outperformed it in 2 data sets, which means the self-supervised learning methods are capable of extracting robust feature embeddings without using labeled data. So that's the reason why, especially in recent 2 years, the contrastive learning is very hot, and supervised learning is very hot as well. And to test here some conclusions I have mentioned before. To test the effectiveness of this self-supervised learning in a much smaller data set, they also performed the semi-supervised experiments. Like first, they greatly reduced the size of training data sets. The key here from 1 up to 100 labeled examples per class. Per class means if we have 6 classes, we only have 600 labeled data for the training. And they use this small size data set to train the supervised and also self-supervised learning models and compare their performance. and this procedure repeat 10 times. And the figure 9, I only show you the average F1 scores comparison among CSS HER, this model, and the same architecture in supervised learning and in the random frozen parameters. Actually, for other methods, they choose the very similar trend. And we can see here both the supervised transformer and the SSL transformer show about the same performance when the K is greater than 25, which is a very small data set. But CSS HAR is more robust because it has the minimal variation between different experiments, and also unlike the CSS HAR, the supervised transform model completely fails when only very limited data, like a K is less than 10, is available. So it means this SSL is very helpful in a extremely small data set. Even you only have like 10 for each class, you can get a better performance. And a very interesting thing I want to mention here, like for the user HAR, only have 16 or 15 or 100 samples per class, they can achieve like 80% accuracy, which is very high. And those are some conclusions about former experiments. And the last part is conclusion and discussions. First, I want to say that we can easily apply this self-supervised learning in federated learning manner, which will reduce the communication overhead because you only collaboratively train an encoder, not the whole model, and also allow the personalized classifiers for each user. Actually, this is the main idea behind the metal hair. That paper I presented last time. They follow this kind of scheme. And the performance of supervised learning besides the upper bound, I've mentioned before. And the self-supervised learning is significantly helpful for the training in the very, very small size data sets. And but some questions remains, like what is the best way to process the sensor signals, and how to choose like the optimal length of the time windows, and how to design the design the encoder, how to design the pretest text. Or there are no uniform guidelines for this kind of design. And the last one is the goodness of this self-supervised learning cannot be directly compared, but only evaluated by the performance of downstream tasks, which means it's very hard to compare the fidelity and the rationales between those methods. So you can see from my previous slides, I don't mention the for each method, I don't mention the disadvantages of previous methods and the reasonable or the rationales behind each method. Because from their paper, they only do one thing, is they try to improve the final performance in the downstream task. And then they will claim that their design of this pretest task is better. But there is no clue to really decide whether the self-supervised learning is more effective or more powerful than others. They can draw those this kind of conclusion. So that's all for today. All my representation. Here are some reference. Thank you. Do you have any questions?